Hello, everybody, and welcome to the first of the workshops for the Chipalooza contest. This is an open workshop, so it's not limited just to the Chipalooza participants. And there has been in the past a lot of demand for an analog and mixed signal set of workshops, and so you can consider this is the start of that. So as a reminder, here is the schedule that we set for Chipalooza. We started the challenge launch a couple weeks ago with the webinar on February 16th. On March 1, we got all these proposals back, and after a very busy 4 days staring at many proposals, we sent out the acceptances on March 5th, posted them to the Slack channel. And so that brings us to today when we're doing the first of the workshops, and the schematics are due on March 22nd, and that gives 15 days left for schematic design and simulation, which, yes, we know it's a tight schedule. And beyond that, we will have design reviews starting on March 25th. There are 40 teams right now selected for the Chipalooza challenge. That means 40 design reviews, and even if we limited that to like 30 minutes each, it is going to cover at least 2 days. So I expect there will be a little more time for some. Now, schematics due means that I want the things finished up and done with simulation and characterization. And there will be a Git repository. I'm going to go over how that's done. And that means whatever you have gets pushed on March 22nd to the Git repository. That doesn't mean that you can't make little tweaks and changes if you have last minute stuff to do between then and your design review. For the design review, I assume that I am going to do something like put up a Google form to let people select a slot, and we'll get that up as soon as I can figure out how to do it. And the layout is due on April 15th, and so that gives you, from the date of the schematic design review, approximately 23 days for your layout and verification. And finally, the reason that the schedule is so tight is because there is a shuttle run that we're trying to meet. The close date on that shuttle run is a fixed date of April 24th. And so not only do all of these things have to be done, but the goal of the challenge is to produce IP blocks. That's not a full ChipIgnite slot. So somewhere between April 15th when the layout is due, or April 17th when the design reviews are done, and that tape out, I need to go put all of these design blocks into one or more ChipIgnite slots and prepare them for the tape outs. So yes, the date is coming up fast, both for schematic design and for layout. So the goals of this workshop, I would call this not just schematic and simulation, it's really set up schematic and simulation. So the first thing I'm going to go through is how do you set up all of the open source tools. I think that's actually one of the biggest questions for people just getting started on the open source tools, is they want to do some kind of analog mixed signal workflow, and they need to know what tools do I use and how do I get them and how do I set them up. For the challenge specifically, then you'll want to know how to set up the Git repository. I don't expect analog designers necessarily to be all that comfortable with Git, so I'll go through that just to make sure that I'm being pedantic about making sure that that whoever is out there, whatever skill level, gets the information they need. And that will be followed by telling you how to set up the file system. That's not set in stone. There are several methods you can use, and I'll go through those. I'll say a little bit about how to use Xscheme and how to use ngSpice. Both of those are they have their own videos, video tutorials, and online documentation. I will spend more time just pointing you to the references that are there rather than trying to spend the time, which is pretty limited with only an hour, to show you exactly how to use Xscheme or ngSpice. Then there is, for the whole analog flow, which I'm going to get to in a later slide, this whole idea of a system that does all of the characterization for you and spits out a data sheet at the end. And I'm going to introduce you to a system that probably few, if any of you have heard of before, called CASE. So quickly here, what is an analog and mixed signal design flow? And more specifically, what is an analog mixed signal design flow? What does it look like in an open source environment? Here are what I consider the components of a proper design flow. Obviously, you have schematic entry and you have layout tools. Parameterized cell generation is generally something that in commercial tools, or more precisely in commercial PDKs, is just part of the PDK. They give that to you. There are those formats being proprietary, they don't exist in the open PDKs. And so we have had to go do all that stuff ourselves for K-Layout for Magic. Schematic capture and layout extraction are a given, but again, these things, schematic file formats are proprietary and proprietary tools. So we have our own formats. So we have our own schematic capture. We have our own way of doing layout extraction. Analog simulation and measurement, that's pretty much a given. Digital co-simulation is something that is been more recently developed for the open source tools. There had been some ways to go about it for the last few years. I think with the most recent push of ngSpice version 42, there is a really good co-simulation capability in that, and that is well worth looking into. I'm not going to spend much time talking about that, mainly because of all the IP blocks for the Chipalooza challenge. The vast majority of them are analog only. The only digital for them would be things like static inputs like trim bits or enable signals. You don't need digital co-simulation just to set an enable signal. The one that would likely need co-simulation is the ADC, and I may get together with the group that's doing the ADC, and we'll try to figure out how to get the digital co-simulation working right. Then when it comes down to verification, physical verification, there's DRC and LVS. I'm going to be giving an entire workshop later, one on layout and extraction, and then another one on physical verification. So I'll cover those later. And then finally, this idea of automatic datasheet generation, for which we've got several options, and I'll be going through those later in the workshop. So going back to the slides that I gave for the workshop launch, for the challenge launch, there were 3 rules related to this part of the design stage, which is the schematics and simulation. First one, I want to make sure everybody understands well, is that designers will use open source tools for the design. No proprietary tools. The main reason for this is that we want all of these IP blocks to be reusable. If everything is open source, then what you have for your IP block is up in a Git repository. If anybody wants to reuse that, all they need to do is clone the Git repo. Inside that, if you're following all my instructions about how to format everything, then all the tools they need to fully characterize that and reuse it in another context is all in the Git repository, and all they need to do is clone those tools, and they should be able to get exactly the same result as you got when you designed it. And as I said in the launch webinar, open source tools also ensure that everything that you put up in your Git repository is legal. Second rule for the schematic stage was that designers will create a public Git repository, and I'll go through that. I'll just show you how to do that live when I get around to that part of the workshop. And the repository must be in a state where at the time of the schematic design review, that all of the files that we need to do a full characterization are pushed to that Git repo. And if we need to help you with anything, it's best that you have all your files in the Git repo, push when you have changes, push often. And when anybody needs to help you, instead of sending them screenshots and saying, oh, here's an error, you can just point them to the repo and say, do this, and you can reproduce the error. That's called a reproducible result. Always good when debugging or when asking somebody else to help you with debugging. We will specify the file system structure, and that's part of this workshop to show you what that is, define it for you. And as I said, schematics will be subjected to a design review, and the test benches, you need test benches that will simulate all of the specifications that we've given to you in the block in that spreadsheet, which you worked from to when you were choosing your block for the proposal. And all of the test bench results must meet the specifications at the time of the design review. All right, now I am going to go into the more live action part of this workshop. I'm going to move from a full screen view to a window view and go through each of these at a time. So step number one is to get the tools and the PDK. So there are two methods or three methods, depending on how you count it. One of them is the Docker container or Jupyter notebook method. And the other one is to do some kind of local build and install. And I said two or three because you can do a local build using this method, which will drop everything into your home directory, or you can do a sort of standard build in which you get each of the tools and do a sudo make install, and it will install it into the structure, the OS file system. So if you are familiar with Docker's containers and you're not happy with or not comfortable with compiling all sorts of tools from scratch, then you probably want to go with the Docker container method. If you're comfortable with compiling tools from source, but you don't have access to super user privileges on the computer you're on, then you probably want this method. And the one thing you do not want to do is something like sudo apt install of the tool. All of these tools, all the open source tools, they are under constant and rapid development. If you do a sudo apt install from an OS package repository, you're likely to get something that's at least a year out of date, and it is probably not going to work. The one possible exception to that is K-Layout. I think they have a pretty good updating. On the other hand, the package manager for the OS is usually related to whatever OS version is. So if you wanted the latest version of the packages, you need to make sure that your OS is up to date. And so I generally don't recommend that. I recommend compile things from source. You either use something that is like the IIC OSIC tools here is kept well up to date, and this is just pulling things from the Git repositories, so it is going to be up to date. And just briefly, the other one is I'll go over that in a minute. Let me just show you the repositories here. So if I go over to GitHub and IICJKU, so this is stuff that was made by Harold Krettel and his group at the Johannes Kepler University in Austria. And if you go to that GitHub page, the first two of the popular repositories here are the ones you want to look at. So the one on the left, IIC OSIC tools, that is the one that is a Docker container or a Jupyter notebook. You can go through the README and find the installation instructions for that. This is the list of tools that are provided in that. It is a long, long list of tools. You probably will not need most of these for the analog design phase, but it will include all the things that you do need, such as it's got, what is here? Well, for one thing, open PDKs and the Sky 130 PDK are in there, Xscheme, Magic, NetGen, K-Layout. So everything that you're going to need is in here somewhere. If you want to play around with some more advanced things like automatic analog layouts, they've got Align. But given the time frame, if you don't already know one of these systems, then you're probably better off doing your hand design. Going back up here, the OSIC multi-tool one, that's for the local install. There's really nothing to this except a bunch of shell scripts, and the one that you want is the setup script. And if you look through that, it's just doing things like, here we go, install xscheme. It just does a git clone and configure and install. So that's all it's doing. Then as I was talking about, if you want to do a sort of standard install to the OS, you can go over here to Open Circuit Design, where I put up a new link called Analog Flow. If you click on Analog Flow, this is my eFabless recommended open source analog design flow. And it says more or less the same thing. It's got a section for each of the tools: Magic, xscheme, NetGen, tells you where to find documentation, tells you how to download, what you need to do to install, and a little usage information at a minimum. And finally, down at the bottom of that whole page, I have 3 appendices for the quick default installations. So I have one set of install instructions for Ubuntu and Debian-like systems, another for CentOS, Fedora type systems, or Red Hat, and then one page for Mac OS. So if I look at that, it really just looks like the same script for OSIC multi-tool, except that it's calling sudo to do all the installs. So that's how you get the tools, and those are the recommended tools. The ones that are listed on this page are the ones that you will definitely need, and the ones that were mentioned on the IIC OSIC tools is a fuller set that you may want to look at, and each of these is a link to where you need to go to find that if you wanted to look at any of these individually. So now this thing about the automatic datasheet generation. I know of 2 systems right now. One of them is one that I developed myself called Case. It was developed about 5 years ago or so on the eFabless platform. And the reason it's not very popular is because it was restricted to the platform because I was using it with the XFAB fabrication process. And so some of that was semi-proprietary PDK information. And so all of it was pretty much restricted to the platform. And then after that, we did actually go through one challenge with that, which was very similar to the challenge that I'm doing now. So we had a challenge in which we asked people to design just a single block, a band gap for the XFAB process using our open source tools that we were hosting on the eFabless platform, and then to characterize them using this system called Case. And after that, we didn't do any more challenges before we got into RISC-V. After that, we got into the OpenPDK, and the OpenPDK has enabled the ability to pull this thing off platform and make it work with the OpenPDKs. So I'm hoping that can gain traction. Meanwhile, there is this really nice system that Karsten Wolf created called CIC. This is the GitHub repository for that. So if you go back to GitHub and Wolfern, this is Karsten's page on GitHub. The 2 repositories that are at the bottom of the section called pinned are CIC-SIM and CIC-Conf. So CIC-Conf is just a couple of scripts that, in fact, there's very little in this except like a couple of Python scripts. And that will set up your file system for the CIC-SIM. And then CIC-SIM is the one that does all the characterizations. I'm not going to go into this, partly because I'm not as familiar with it as I am with the system that I wrote, but they are very similar, and what I'm describing is going to be quite similar to this. You can choose either system that you want. If you want to use that for the characterization, that's fine. Then for Case, that is under eFabless. So if I go back up to GitHub eFabless and Case, that's where you find the Case system. It's also just a bunch of Python scripts. Notably, though, it is not yet, I have posted that fairly recently, so it's not yet part of the OSIC tools. And so if you get it, you're going to have to do that separately. All right, now switching back to the Git repository. So when you are working on your project, you will need a Git repository to push files and data to. And the first thing you need to do is to name your project. So I recommend following the naming convention that Google came up with when they were doing the open PDKs. If you follow that convention, then your IP looks like just like IP that's in the PDK. So if I had, for instance, if Skywater had given us a set of analog IP, then we wouldn't need to be doing this challenge, but we would have had something like a library called Sky130_FD for Foundry underscore analog, say, and then it would contain all these analog blocks that would be called Sky130FD IP and then the name of the analog block. Instead, I've started doing a few of these myself. I've been naming them EF, that's for eFabless. So I've got Sky130_EF_IP_, the double underscore is significant according to the Google notation. And then something to uniquely identify that block, like RDAC 3V 8-bit or Instramp for an instrumentation amplifier. So just choose some unique handle. It doesn't have to be 2 characters, but use like your initials or something for that, and it'll be fine. And the default option for Git repository, it doesn't really matter what Git repository it is, GitLab, GitHub. The default option would be to use GitHub. GitHub, of course, is where the vast majority of people keep repositories of things. So, and there are several ways to do that, either to create it on GitHub and then import it, or create it locally and then push it up to GitHub. I'm just going to recommend this. Create the repository on GitHub, import that repository back to your computer, and then you can place files in that and then push them back up to GitHub. And you can let GitHub create the README and license files for you. So I'm just going to show you, in case you're not that familiar with Git. So I go to my GitHub account, which is R. Timothy Edwards. And good, I've been having troubles with this. It is going to let me create a new repository. So here's a little plus button up here. I click on that, create new repository. So I do new repository, and I'm going to choose my repository name. I'm going to call it Sky130EFIP example, say, and give it a description here, Chipalooza challenge example. I'm going to keep it public. I will let GitHub add a README file for me. I'm going to fill that out later with a description. I mean, it's going to start out with whatever I type into the description line, but I can fill that out with the description of my circuit later. I don't recommend getting the git ignore from here, which is like 100 different choices for different tools, none of which apply, but I do have some examples already up from which you can get a git ignore. So don't do that for now. Choose a license. The standard license, or what people consider the best standard license for open source hardware, is the Apache license 2.0. And then I click on create repository, and I have got that repository ready. So in my local directory here, I'm going to create a directory called Chipalooza 2024. I'm going to cd to Chipalooza 2024, and then I'm going to do a git clone github.com R. Timothy Edwards. And I just called it Sky130EFIP example. And now I have got my design. Now, I said you should put a, let me go ahead and advance the slides here because I'm mentioning all the things that you need to do next, which includes that git ignore thing. You will need to set up the file system. Again, if you're using Karsten Wolf's CIC system, the setup of directories is a little different. Just you can use his the configuration tool that does this for you, and it will create those directories. I would recommend at least for the purposes of the schematic part of this workshop, make yourself an Xscheme directory. And if you're using the case system for characterization, make a case directory. So make dir Xscheme, make dir case. I'll get around to the .getignore in a minute. Let me jump forward to another slide. So there is a set of examples that I have in my directory. Again, that's github.com/rtimothyedwards. I have, where was it back here? One is for this thing called the instrumentation amplifier, and the other is the RDAC, resistor ladder DAC. So I would suggest that you clone those. You can use those as examples. So I'm going to do a git clone of the instrumentation amplifier and the RDAC RDAC 3v_8-bit. All right, now I have two nice examples to work with. If I go into the Sky 130, either one of them, look at the .getignore file. So the general idea here is that you may have lots of working files, but you don't necessarily want data files like raw files to be up in the Git repository. Keep the Git repository to a minimum amount of data, just the amount of data that's needed for somebody to download and completely reconstruct all of the data that you need for characterization. So I have got the case system set up with ngSpice as the working directory where it creates data files and all of its temporary files. And I'm excluding that from what I'm posting back up to GitHub. Then back here, so of setup files, I have two things to do. The main one is in my Xscheme directory. I want to have, let's see, actually, I do want to do that here. I was going to do this in the example, but I need to do it here too. So I'm going to copy from the PDK the Xscheme.rc file. So that's under, well, for one thing, I do need to set, it's one thing I can do is to set an environment variable for PDK root. There are a number of tools that require it. Most tools, I think, by now have been developed so that they don't actually require it. They can just figure out where the PDK root is because it is generally in one of a few known places. But let's just say I'm going to set PDK root to user local share PDK because I've done the standard install. And just in case, set my PDK here to Sky 130A. And then I'm going to copy from the PDK. This now PDK root, PDK, and libs.tech Xscheme.rc. So now I have a copy of the Xscheme.rc file in my working directory. There's one other thing I want to do, and that has to do with the fact that I'm going to have schematic files in two different directories, one for case for the characterization and one in my local file for what I'm doing. And since I've done this in a slightly oddball way, but I have made all of my symbols relative to the root directory of my project. So I'm going to, I'm going to add the root directory of my project to the Xscheme library path. This is the path where Xscheme searches for things it's looking for. Anyway, the main thing is that I'm not even sure it's needed here really, but definitely in the test bench files, the test benches need to reference your schematic for your IP, which is over here in this directory. So if you've got Xscheme files in different directories, then you need to modify the Xscheme.rc so I can figure out where they all are. So this is going to be my local working directory. This has nothing to do with the characterization per se, other than that I'm definitely going to need some of these characterization test benches so I can do my design and test it. But for instance, here, I've just got my own test bench here. So if I do Xscheme, if I've done everything right, the Xscheme should just come up and run. But actually, if you do want some help with Xscheme, the actual best way to do this is to start Xscheme. Once you have that Xscheme RC in place, it knows where the PDK is. So it's all set up for the PDK. If you then start Xscheme without giving it a schematic main, then it brings you to this page, which is really nice. This is something that Stefan Schipper's put together. And it has lots of examples on how to run Xscheme. So for instance, I can go over here and there is a example of how to do a sweep on a MOSFET. And if I click on that and type E to enter, then here's a little test bench that tests the IV curves on a MOSFET. And you can follow them. It's just like a built-in tutorial for the Skywater process, and it's wonderful. But here I am already halfway through the time for the workshop, so I'm not going to be able to demonstrate how to use Xscheme. There are video tutorials for that. There is online written tutorials for that. So let me go back to just starting with the test bench I had. So again, if I've set up everything correctly, then I should only need to do a netlist. And I can simulate what I have here. So this is my working file. I wasn't even using Xscheme's graphing capability, which is pretty nice. And you can see this is a pretty bad example. I have, this was not intended to be a good example. It was intended to show failures and things for the purpose of demonstrating. You can see that here's the amplifier in a unity gain feedback connection. So it's a source follower and it doesn't quite make it up to the rail. And consequently, it's this is V in minus V out. So it should be sitting at 0, and instead it pops up at the end. So you'll see that in the characterization a little later. But anyway, everything here is working fine. And I ran through a few things really quickly there. Was using the netlist button to create the netlist, the simulation button. So all of this is working manually in Xscheme locally. The setup here is I've got 2 files. I did not use the code shown, so I have to go click on Q for query to see what's in them. But this is my control block for ngSpice. I'm doing a transient simulation and doing some plots. That's all it's doing here. And then to use the Skywater PDK, all I'm doing is using the .lib file, and then I am giving it the path to the sky130.lib.spice and telling it to simulate in the typical corner. And if I do everything manually like this, I would have to do this over and over and over again for different corners, different temperatures, different voltages, and I would have many test benches, or I would be implying that every time I want to do a different simulation, I have to go in and change something manually, save, do a simulation, get results. That's why it's very, very helpful to have a system that does all that automatically for you. Yes, so now I'm getting into the whole thing about how you get it to automatically do these things for you. So the 2 design examples that I pointed to and cloned into the system here are both set up for using this case. And the way case is set up is there are certain directories where you create all your files. And the ones I've already shown are Xscheme, where I was doing all my local work and has my project schematics in it. Then there's another directory called case, and that will need to have a characterization file in which I will tell it how to do the characterization. And then I will provide a whole bunch of test bench schematics, which are the schematics that are set up for doing all these different test benches. Case itself will create several directories. One is called netlist, and that's where it will do all of the extraction, schematic capture, and produce a netlist into this directory itself. And likewise, you'll do schematic capture from the test benches and drop them into ngSpice, and that's where it will do all of its simulations. Then the trick is this characterization file I mentioned is to get the information that we put into that spreadsheet for each of the IP blocks. We gave you a set of specs. So these are the specs, and the specs are what go into this characterization file. And I apologize that my slides keep switching back between one IP block and another. So if this is, for instance, the ultra low power comparator, then you may have a design project called Sky 130 My IP ULP comp. And so this file is going to be under the case directory and the name of the project followed by .text. The characterization file, there's more to it than this, but for each of those specs, there's going to be one block in that file. And you can use the example files in the two example directories that I pointed to. I'll show you how it all works in just a minute. But for each of those electrical parameters, there's going to be a section. It's fairly straightforward. In the specification, I've said, all right, for this particular electrical parameter, there's perhaps a minimum value limit, a maximum limit, a typical value. Normally, you'll have something like a requirement that the maximum value is the absolute limit. If so, then if you exceed that, then you're failing spec. So I would put maximum for the maximum value, put the value in here. In this case, it's measured in percent full scale range. And if I want to make sure that the tools are showing that the circuit fails spec, then I'll write fail after it, meaning that I want to use this to show that it is a pass-fail result. Likewise, for typical, I just say, all right, by putting the word typical in here and giving it value, it's just a reference. It will measure that and display what the typical value is. I didn't put fail, so it's not going to fail the circuit if it's not exactly my reference value that I put in. Then you tell it how to simulate. I have got this thing set up so that it doesn't have to be using ngSpice. That is the one that I have been using, and so the one that's most likely to work. But I'll just say my tool is ngSpice, and I will give it the name of the test bench netlist that it's going to use for that. And the format, so I like to set up all my test benches so that they produce ASCII data rather than raw files. Because of the way this format is, it can use raw files too. I just find the ASCII data is better for test benches. There's a limited amount of information you're writing. It's just measuring what you want to measure and writing that out to a file in row column format. Once you get a result, there are two stages here. You simulate, you measure. If you need to do something complicated for measuring, you can add a section down here called measure. You can pass all your results to another program like MATLAB. I'll show you an example of doing that. That's in the DAC example, has one of those. And otherwise, if your simulation is just producing one result, like a value for current or a value for voltage, then all you need is a single result. The measurement, there is no measurement, it's just a value. All it's doing is it's going to collect those over all of your conditions. It's going to simulate over each of the conditions, get that value over all those values, over all conditions. It's going to pick out what's the maximum value, what's the minimum value, and what was the value at the typical condition. And that's what goes into the results. So my condition, so then I have to list my conditions. What conditions do I want to measure at? In this case, I'm measuring at 3 temperatures, high, low, typical. I'm measuring at 3 process corners, slow, fast, typical. And I'm measuring at 2 different common mode voltages here that are the 10% and 90% value ranges. Yeah, let me just, before I go do something live with this, let me just show you. So the test bench will look something like this. Again, I flipped to another test bench here, which is for CMRR, but it's all the test benches look more or less the same. The test benches are about as simple as you can get. You don't want anything particularly complicated, just to simulate PSRR, CMRR, or input offset voltage. The main difference between this and the test bench I was using before in my working directory is I have gone through and I have replaced lots of values with variables. So for instance, here I'm looking at the VSS value. So instead of being DC0, it is now DC, and I'm doing this by putting the value in braces, VVSS. And that goes back to one of these values back here. So all of these values that I have for conditions, like VVDD, they become values that go into variable names in here. Then Case takes this test bench, schematic, it creates a netlist out of it. It takes that netlist and it goes through and it substitutes the variables with values for each of those conditions over all conditions. So for instance, here, if I have 3 temperatures, 3 corners, and 2 values for the common mode voltage, then I get 3 times 3 times 2, which is 18 different simulations out of this. And it's going to create then 18 copies of this test bench, substitute the values for those, and simulate them. And the result from all that goes into this view. This is what the Case GUI looks like. And once you have simulated all those parameters, you get everything in nicely. Green means it passed, red means it failed, and then you can go through and look at where your failures are and know exactly where you failed to meet spec and by how much and what you need to do to fix it. So now I can go to my live view and show you how that works in practice. I am going to leave off that example one and look at the, let's start with the instrumentation amplifier, which is really just an op amp. And I'm going to go, so if I want to run Case, I did clone Case earlier in the workshop, so it's there down in Case. Okay, I did not clone Case. Let me do that. So git clone .com ethablets. All right, I'm not sure what I did wrong last time, but there it is. I cloned it. And in here, there is a lot of these things can be run as command line functions, but if you want this view here with the nice formatted output, that's the Case GUI. And before I run Case GUI, let me just show you live what is in this Case. Oh, wrong one. In the instrumentation amplifier Case subdirectory, the text file. So this is the characterization file that I was mentioning. There is more to it than just the all the test benches and electrical parameters. So the best thing to do is to start with a copy of this, like from one of these 2 example directories, and then follow the format. You want the name of the project, a little description of the project. Once it's gone up in GitHub, you can put in a GitHub commit number for it. This tells you what the PDK is using. Case format right now is format 4.0. There's an authorship block, so you can claim authorship of your IP block. And you know when the creation date was, or you can put in a modification date and what the open source license for it is. After that, there's a block with paths. So you can tell it, where are all my schematics? Where's my layout or magic files, layout in GDS if you're using KLayout, say. And then for the use of Case, where Case is going to put netlists, where it's going to have its test benches, and where it's going to do its simulations, where it's going to put plots. You can combine and reuse different blocks. So if I have another repository that I need to pull something from, I can just put it in dependencies. There are no dependencies for this amplifier, so I don't have anything in this block here. I do have one for the DAC, which I can show you in a minute. After that, there's a section for pins, so you can declare the pin out. So all of this information is what you need to create a data sheet. And if you look at any kind of professional commercial data sheet for a product, it will have, first off, it'll tell you what all the pins are. It'll have a whole section on what's the pins, what does the pin do, what are the maximum minimum limits on the pin, and that's what information goes into this block. And then again, a commercial data sheet will tell you or here are the electrical parameters, and then there's usually a note that says, if not otherwise specified, all these parameters are taken under these default conditions, and it will list you the default conditions. So here's a section that matches that in a data sheet. You've got your default conditions. It says, here's a value, and if I don't otherwise specify it, it is going to be this value. So for instance, VDD, if I don't otherwise specify it in my test bench, it is going to be set to 3.3. And that is followed by all of the electrical parameters that I want to measure. And each one of them is going to be given a unique name. I can give it a description. I can say what I want the result of that to show up as in my display over here. It will be in some kinds of units. Whatever I specify for units is not just a string. It actually pays attention to this. If I say I want it in microamps, it will produce an answer in microamps. Then I tell it, what is my spec? What is my minimum and maximum? I already went through that. Write fail if it is going to cause the circuit to fail spec. And then I tell it, what is my simulation tool? What is my template netlist? And what kind of format is my simulation producing? You'll notice I've got null in here. I like to use the wrdata command in ngSpice. Here's the ngSpice user manual if you want to look at the different commands. Here is what I'm using, wrdata. And it writes out things in ASCII and column format, which is nice, but it also likes to just decide for itself what should go in the first column. So I often end up saying the first value is a null result, and then the second one is the one I actually want to look at. The result is the thing that Case is going to pay attention to. So it's what I'm telling it here is that the simulation is producing an output file. That output file contains two values. I ignore the first value, and the second value is my result. And then I made this one very simple so that it simulates really fast. I am only simulating this one at 3.3 volts VDD, typical corner, typical temperature, and 3 different values of VCN. So now let me go ahead and run it now. You just saw what the entry, that was the total entry for that condition. So if I'm going to go into the instrumentation amplifier directory, and this is where I want to run Case from this top level directory. Case itself I had put into a subdirectory over there, and I want to run Case GUI. So I'm going to run case-GUI.py without any arguments. It will find that text file and it will read it in. So now I've got this whole list of all of my electrical parameters and what I need to do to hit minimum maximum spec. And for each of these, I just wanted to click on simulate. The one I just showed you was the one, remember the display was IDD. So this is doing DC current through VDD. And if I press simulate and run, it is going to run all of those in parallel. And so I've got all this in multiprocessing. So it will run as many of those simulations in parallel as it can and produce a result. So you can see I've got this at minimum for maximum. Maximum is 110 microamps. And if I can see it says pass. Pass is actually a button here. If I click on that button, then I get a table form of my results. And it says that, oh, here are the results that I got over these conditions. And this is not particularly interesting because there are only 3 results here. But if I click on VCM, I can get a graphical view of that. So now it's plotted as the result output, the current versus VCM. Now I can go back to the table view. So that gives me some more information on, if I have a failure in here, why it failed, and on under what conditions it was simulated, and under what conditions it passed or failed. So let me close that out and do a quick edit of that. So let me go back to the first of those electrical parameters. So let's say I want now to simulate over all temperatures from negative, not all temperatures, but at maximum minimum, go from 40 minimum to 100 maximum. So now I'm simulating at 3 corners, 3 temperature corners, and then 3 process corners. So I'm going to go from slow to fast corners. And I'm going to simulate my voltage supply at minimum of 3 and maximum of 3.6. There. Now I will start up the GUI again. And now when I run the simulation, it will run over not 1, but 27 corners. And I think it is fast enough that I can do this in just a few seconds. So give that a little time to run. There we go. And now I can see that if I have simulated over all corners, I'm actually failing at the maximum. And if I click on fail, now I've got a list of all the simulations that it just did. And the results are ordered bottom to top. I can click on this to order them top to bottom, and I can see that the 2 that are out of spec are here at the fast corner. Not surprising, the highest current was at fast corner, the highest current was at the highest temperatures and the highest voltage. So clearly, if I want to meet this spec, then I have to tweak my circuit to make sure it doesn't fail at these upper corners. And that's how I use the case system. A couple other things that I wanted to point out was that for the RDAC, it has an example in which if I look at the case report for that, whoops, I just passed that. This has a dependency. So I've got another repository up there called sample and hold. And the sample and hold is part of this DAC. And by putting it in the dependencies, case now knows where to find that and make sure that in fact, if it cannot find it, it will actually clone it. So if I run case now, on this, and I think this should work if I do a simulation. Yeah, it looks like it's working. Yep, and it gave me a result. Now, to do that, it had to do multiple things. It had to find out that there was a dependency. It had to go do a git clone of that dependency and install it. And then it had to run xscheme to do a schematic capture of my netlist. It had to run xscheme to do a schematic capture of my test benches, and then run all the simulations and collate the results. So all of that it did in just a few seconds. Now, so I had specified, sorry, not what I wanted to do. Case, just look at this once again. The dependency, I have set the path as ... so I should be able to find this now. It should have cloned that into here. And in fact, yeah, you can see it. It just cloned that into my directory here as part of the process of trying to figure out the characterization of that circuit. So that's what I mean. If everything is in the same format up in these GitHub, then you can make the tools do all this stuff automatically. You can say, I am using the sample and hold as a dependency, and you don't have to worry about the fact that, and you don't want it in your repository. You don't want to make an entire copy of it. You just want to use it. So you say it's a dependency, and then the tools take care of the rest. And so that's pretty much, we are coming up close to the top of the hour, and I want to leave just a few minutes. I'm probably not going to have time to answer all the questions that people have, and I haven't even been paying that much attention to what's going on in questions and answers. Andy, if you have been paying attention to Q&A, are there anything there that should be answered live?
There are a couple we should probably try to hit straight away.
Sure.
The first most obvious one is it looks like everybody wants the video recording and the files that you showed. And so the question was, when will the video recording be available? Jeff?
Yeah, usually I get some help on that, but yeah, we'll get it out in the next day, tomorrow sometime. We'll be out.
Yeah, right. We'll try to get out the next day. Andrea is the one who usually does this, and she's on vacation, so it might take an extra day. But at least for the slides, I'm responsible for that part. I can get these slides up on the Slack channel today. In fact, I'll do it right after this.
Next one was very simple. It says, is there a virtual machine available for the open source tools?
Well, there are Docker container versions. I think you would then be responsible for your own virtual machine, though, right?
Yes, right. Yeah, the Docker. I think the Docker container is probably the closest.
Okay,
recommended.
Right, but is there like a virtual machine that you recommend? I know there are some that you can get for free. Are there any that you can get for free that would be capable of doing all of this stuff?
I'm not sure. I think we have to follow up on that.
Yeah. Take that one offline. Okay, anonymous attendee asked, is the file available right now? The answer is yes. So Tim's going to make that available literally immediately after the meeting. Okay.
Yes.
I believe you mentioned cloning the Sky 130 RDAC repo as a reference. Where can I find this?
Oh, yeah, that was just right here in my directory. Is where is it? This one. So it's github.com/r.timothy_edwards/sky130ef IP RDAC3v_8-bit. So if you, well, it's not, I have a number of repos. So if you just went to R. Timothy Edwards and look for it, you have to go click on projects and then, no, not projects, repositories, sorry, my fault, and find it down in here. So there it is.
Perfect. Okay, Chris Meyer asked, when will these configuration files be available in a text file so we can copy? The answer is they're available already.
Well, the ones here are available, and I chose the instrumentation amplifier and the RDAC because that covers most of the things that most people need, like CMRR, PSRR, like current draw, like power draw, and so forth. I think that covers the majority of things that people are going to need. There will be more that I probably don't have listed, and some of them you'll just have to make yourselves, or I can probably help with that. So if you need something, a characterization file, and you're missing a characterization for some kind of parameter, and you don't know how to do it, come to me, I'll help.
And answering live, if we have tools set up with another user's VM, that should be okay, right? The answer is yes, as long as they're open source tools. And no proprietary tools, no proprietary PDK, no proprietary content. And Chris Meyer, it would be helpful to have a minimalist version of the top schematic just in case you're missing something. Ask me how I know, question mark. Okay, thank you, Chris. Piece of advice there. For setn PDK root, which programs use this variable?
They all do, actually, as far as I know. I know Xscheme does, Magic does, ngSpice I don't think cares.
Yeah.
And both Xscheme and Magic right now are set up that they will figure it out on their own, even if you don't have it set.
Can case be used with things other than Chipalooza?
Yes, although it has not been used much on the platform. As I said, we had it set up for the XFAB process on platform.
Yep.
But that's sort of sunsetted now. So right now, probably the only people using the case system are you, if you choose to use it.
Yeah, if you're using it outside of Sky 130, yeah. Can you use JKU OSIC tools Docker?
Yes, absolutely.
Okay. Tiny Tapeout has a VM currently online that has the tool suite. Yuri Shaket is pointing out. Thank you, Yuri. Yes, and I've actually used that VM and it works. I use that VM image as the very first VM image I ever set up, so thank you.
Oh, very good. Yeah, all right. Thank you for that.
If my design uses external blocks like the bandgap reference voltage, should I simulate it with case as an external dependency?
Yeah, maybe. I mean, it depends. Like for a band gap, are you going to have access to the band gap circuit? The problem here is that you may be depending on a circuit that hasn't been designed yet. So I've been telling people, oh yeah, you can assume that you've got a band gap voltage coming into your block, but if that circuit doesn't exist, then you're probably just going to be simulating it as like an ideal voltage source or something like that for now. In principle, yes, there would be a band gap somewhere. You would treat it as a dependency. I don't think that dependency is going to exist for you, though, in this case.
Not early enough, anyway.
Yeah, not early enough.
The questions are arriving almost as fast as we're answering them.
Well, we'll just choose a cutoff. We could probably like go till a couple minutes after the hour.
Though we may be missing something shown here, is case is the same as CIC sim.
No. Well, it's equivalent. I'll say that. Both of them will take a file. In the case of CIC sim, it uses a YAML file. In the case of case, it uses JSON or a text file of my own format. In both cases, they are set up to declare your variables and to make substitutions into a test bench file, which is set up with variables in a way that is absolutely not ngSpice compatible, but is known to both case and CIC. And I've been working with Karsten, so I've been trying to get our two systems slightly more aligned so that the syntax is more similar between them. But they're still separate systems and will have slightly different syntax.
Anonymous attendee asked, what should we put instead of EF? Because that's free fabulous, right? The answer is yes, that's free fabulous. A letter sequence, preferably 2 or 3 letters, not 10 letters, that allows you to readily distinguish who provided the set of IP.
Yeah, like your initials.
Yeah.
Would be fine.
Exactly. I see Verilog folder in the repo. What does that folder do?
Well, that is not going to be needed for this challenge because you're only generating a block. If you want to simulate it within a full chip system, right now, I mean, I could go into this for like another 10 minutes, but which I want. But there are various ways to do a full chip simulation, but most of them involve starting with Verilog. And while co-simulation right now works when you have a Spice file and you want to simulate some Verilog block as part of that, it's not set up to simulate like a giant Verilog block with some little Spice block inside it, which is actually what you want. If you have your analog IP and the rest of the system is this big digital system, then you'd really like to just simulate that little block in Spice and the rest in Verilog. Because that doesn't work, my favorite method is just to create a little Verilog wrapper for the analog block. And yeah, you're free to do this. If you want to look at the example I did there, it's a fairly standard example in which I just describe the function of the amplifier as just, I think the whole function is just input. I declare the analog inputs as real variables in Verilog, and then I just say output is equal to 1,000 times input P minus input N. So it's not trying to capture any of the analog artifacts, but just say, all right, this is how an amplifier kind of works if you treat it as an ideal thing. And that's enough to give you functional verification inside of a larger system like an SoC.
Got it. So I've got about 10 more. I'm going to try to go through them as fast as I can. Can case handle Monte Carlo simulations as well?
Oh, yes, it can. And if I weren't so pressed for time, I would show you. If you go to which one? I think it's the instrumentation amplifier.
While Tim is looking, I'm going to say, are there going to be other analog mixed signal or analog challenges in the future? The answer is definitely yes. Our next immediate challenge is most likely to be a generative AI challenge. So the next challenge we're going to run, but we're absolutely going to have a rotation between analog, digital, and analog mixed signal going forward. And we might actually have analog, digital, analog mixed signal, and flow or development methodology as the set going forward. We're trying to decide on the fourth bucket. whether there's enough people in the community that would be interested in that. Thank you, Ugur.
Yeah, and then the answer to the Monte Carlo question is it's here in the RDAC example. So I've got one simulation where I'm just calculating INL on corners, integral nonlinearity on corners, and then another example where I'm doing it in Monte Carlo. And I'm not going to try to run that live because it runs a bunch of simulations and I'm not going to wait that long. But the nice thing about it is where before I was clicking on the output where it said pass and it would give me a table view. If it's a Monte Carlo, it automatically detects that and it'll give you a histogram.
Anonymous attendee asks, how does CASE know which simulations are spec'd to be characterized? As in, where does the table list come from?
The table list, it comes entirely from that text file, and that's the hardest part of it is that you need to go manually convert the spec that we gave to you in the spreadsheet into a text file. And that's the part that I said I expected it to be the hardest part, and I am here to help.
Multiple people asking, is there any documentation of how to do a digital and analog co-simulation? 3 people with the same basic question.
Yes, there are. Probably you should re-ask that question in the Slack channel so that I can go look up where it is. I know that if you go to the ngSpice, I'm having trouble remembering exactly where it is, but I know that I have that reference somewhere. But yes, there are some good examples set up showing how to do it in ngSpice. And then Zeiss has a method for doing, yeah, I think it's it is proper co-simulation. So it can be done in Zeiss as well.
I'll try to capture it in the Slack channel for Chipalooza so people know.
Yeah, I'll post it in Slack.
Christopher Meyer asks, how do you simulate mismatch in the case environment, assuming this probably requires Monte Carlo?
Well, they're in the Skywater PDK, they define, or I should say I define because I created the .lib file, separate corner cases for mismatch. So where I was specifying in my file here what was being simulated at typical, fast, or slow, I can simulate at typical underscore MM or fast underscore MM. Those are mismatch corners, and I would treat them like Monte Carlo. So I would specify that I want to do some number of iterations, and then it will just run that a single corner at X number of times for to build up the list of statistically significant results.
Got it. I got 2 different questions around how to run case. The first one is to get case inside of the JQ Docker. Do I just clone it to /EDA/design?
/EDA/design. I think so. I'm not that familiar with the file system that the Docker sets up, but that sounds right.
Is it just Python?
It is just Python.
Then the answer is right. Okay, good, fantastic. Next
one. Well, the scripts are just Python. You can add in MATLAB, Octave scripts in order to do your computations. Yeah.
Can I run case from CLI and then generate a PDF or something like that? And is there a way to add graphical information to report?
That is something that I hope I can get stuck into it in a few weeks. I do not right now have any way to get to a output view other than this view here. Yes, you can run it by the command line, and you will get an output file that you can read into this and get this display. The one thing it is missing right now is a way to get this into like a PDF or HTML format. Karsten, that's one nice thing about Karsten's system is that he does have a way to just produce a output format in, I think, whatever you want it, HTML or PDF or whatever.
I have logged that in our internal Slack channel, and
it's something I need to do. I don't think it takes that long to convert a grid system like this into a nice PDF.
Somebody asked for the Slack channel live. Normally, Andrea posts it. Can you either post it, Jeff, or Tim? If you could post it live, that would be super helpful.
The link to what?
Chipalooza, the Slack channel that we're using for this, and how to get to it, which repository it's on. It's
right. I mean, the best way to get to it, if you have not registered for it yet, the best way to get to it is just to go to efabless.com. And on the front-facing page of eFabless, up at the very top, there is a little button that says Slack. Click on that, and that will take you to the registration page.
Thank you. And the channel for this particular challenge is Chipalooza.
That's right.
Okay, we're down to two left. Hello, eFabulous community members. Can you share reference resources, GitHub, etc. in the discussion panel window? They'll be on the Chipalooza channel. The person who normally does that live for us is on vacation, so we're trying to cover as best we can. I apologize. And then the last one, I might have missed this. Are we expected to use combined models for simulations? And is there some specific commit to the Open PDK library we should be using?
Whatever is most recent is the one that you should be using, though. If I think like all of the things that I made reference to, like the OSIC, IAC OSIC tools are close enough to now that they should be fine. The combined models are probably better overall just because the other models are discrete, and it's very easy in analog design just to run into a problem where you have created a MOSFET that is just the wrong size and it doesn't fit in a bin, and then you try something like a Monte Carlo simulation or mismatch simulation and it says it can't find the device, and then you're left wondering why. You'll have much fewer of those kind of problems if you use the combined models.
If you want something that works forever in billions of units, you can choose to use the discrete models. It's slightly harder design problem. If you use the combined models, it's easier to do the design. There'll be slightly more variability versus the model in silicon.
That is most likely the case.
10,000 foot summary.
Yeah, that's pretty close.
I think that's it, Tim. That's the
yeah,
end of
we are right. We are 13 minutes past the hour, and I suggest we wrap it up.
Great. Yeah. Thanks for everyone for participating, and thank you, Tim, for presenting. That's great content, and looking forward to everyone's contributions on this.
And thanks for the fantastic question list to the guys in the community. Really, really helpful. Thank you.
Absolutely. Glad to have all of you joining.
Take care, everybody. Bye-bye.
Take care.